Okay, we're back in business. Okay, so here's what we were talking about last time. We were talking about the multivariable chain rule. And remember the big idea, kind of a rip-off of the single variable chain rule, is that you can think about what a function does, like if we look at what f is doing here, and in particular how f is affecting input changes to turn them into output changes, again, not values, but changes. It's a factor. Right? It's a multiplicative factor. And the big idea of the chain rule is that if you have a succession of factors and you're interested in what you might call the total factor, well, the total factor, I think, is pretty satisfying to claim that it's the product of the individual factors. Again, you multiply by 2 and then subsequently multiply by 3. You've multiplied by 2 times 3, which is 6. Okay, so I like to think of the chain rule in those terms, that it's just the pretty satisfying observation that factors multiply. Okay, and applying that same idea in the multivariable setting, well, here, same deal. A derivative is a factor. Asterisk. Okay, yeah, sure, fine. It's something we're multiplying by vectors, and in fact, it's a matrix factor that you're multiplying by vector to get another vector. Whatever, that's details. Don't get lost in the details. The point is, a derivative is a factor. And so again, hopefully not that surprising. When you have a succession of factors, the total factor is, I think again, pretty believably, the product of the individual factors. So that's the way I like to think about the multivariable chain rule. Very intuitively satisfying for me. Hope you like it. Anyway, so I think this is where we left off last time, and so off to an example of how to use this. And there's a fair amount of setup that goes into this question. Excuse me. So all of this is set up. All of this is the statement of the question. There's a lot that has to get said. Okay, so first of all, this is the first function, and then this is the second function, and I claim that it's implicit in how this is written down that we are composing these functions. And you can see that by virtue of the fact that what comes out of f is exactly what goes in to g. So we're clearly composing these functions. Okay. All right, and the composition takes the original inputs as its inputs and gives the eventual outputs as its outputs. Okay. All right. Now, various facts are going to be given, but having given those various facts, we're going to be asked to compute what is the derivative matrix of that composition. That'll be the first part that we'll address. We'll get to that in a minute. And then we will also be asked to compute this particular partial derivative. And notice, this is literally a partial derivative of one of the outputs with respect to, well, one of the inputs of that composition. Okay. All right, now what do we have to work with? What are we told? What specific details do we know? We're told this and this and this. A couple of derivative matrices, and apparently a value of the f function for some reason. It's not yet clear, but we'll get to that in a minute. Okay, so how are we going to go? By the way, we're going to focus first on computing the derivative matrix. We'll get to the partial derivative after. Let's not worry about that just this second. Okay, how are we going to compute that derivative matrix? We're going to come back up to here. Here's our multivariable chain rule, matrix form. Again, derivative matrices multiply when you compose them. Okay. All righty, if you want to compute the derivative of a composition, boom, there you go. Okay. So copying that down over to here. Well, applying it, I'll say, over to here. There's the multivariable chain rule. Okay, some of this falls into our lap. We apparently need to know the DF matrix at 1, 2. We were given the DF matrix at 1, 2. So, boom, that's just that. Nothing to it. That falls right into our lap. Okay, the next one, a little subtle, a little bit of a tricky bit here. We are asked for DG not at the same point, not at 1, 2. The chain rule told us so. By the way, let's think about why is it that the chain rule tells us this? Why is it that the derivative... Let me just shrink. Okay, here we go. Why does the chain rule have dg evaluated at f of a, not at a? And there's actually a pretty straightforward answer to this question. If you look at the df matrix evaluated at a, why is that? Well, because the df matrix takes input vectors to output vectors, and the presumption is that we're therefore going with this velocity, but we're going with that velocity while we are at that point. That point that you are at in the input while you are moving with the given velocity. That's the point where you're going to be evaluating the derivative. You're evaluating it where you are. So, of course, df should be evaluated at a. Likewise, by the way, if you look at the composition here, that composition takes this input velocity and then returns the output velocity of the composition. And where are you when you're in the domain moving with velocity x prime? Well, you're at, again, the point A. And so, again, that is evaluated at A. So with this in mind, why is this matrix evaluated at f of A? Well, let's look at what dg does. dg takes this as the input velocity, gives you that as the output velocity, and y prime is your input velocity when you're at this point, not A. Right? You're at this point right here, which is pretty clearly f of A. All right, so that's it's a weird little thing to have to remember, but pretty natural when you look at the picture and just think about what's actually going on. Okay. All right, so all of this in mind, how am I going to compute the dg matrix at f of 1, 2? I don't seem to have the dg matrix at f of 1, 2. I have the dg matrix at 3, 1, 0. And that's, is that okay? Well, thankfully, f of 1, 2 is 3, 1, 0. So, in fact, the one that I have didn't appear to be exactly what I needed right away. Turns out it is exactly what I need. And so that wrong color. That dg is indeed what I was given. Everybody on board? And you multiply the matrices. Okay, now there's one other little landmine I want to talk about here. Just heads up, it's real easy to mess this up. And when I wrote this example several years ago, I deliberately wrote this example in such a way as to help me distinguish between who is understanding the details of what's going on and who's kind of copy-pasting and working by analogy, stuff like that. So who's understanding this deeply and who's understanding it superficially. Look what I did here. Sneaky me. I gave you df. I gave you dg, but I wrote the dg on the right in the statement of the question, but it ends up on the left in the algebra. And I wrote df on the left in the statement of the question, but it ends up being on the right in the algebra. Now, this is not optional. You have to do it this way. Right? This is the right way to order them. We are, in fact, composing two linear transformations here, right? Two matrices. And the one that acts first has to be the one in the algebra that acts first. And tragically, and blame whoever you'd like, right, for our notational sort of quandary here, but when you draw a diagram, a left to right moving diagram, the one that acts first is the one that's on the left. And again, blame who you like, but when you're talking about matrix multiplications, the one that's on the right is the one that acts first. It is what it is, right? And I've been burned badly on this previously, right? And I've seen students get this wrong as well. So please be very careful about this. Please be heads up. The order really matters. And And what you see in the diagram is going to be sort of backwards in some sense from what you see in the algebra. So, man, be careful on that one. How we doing?
Can you scroll up a bit?
Mm-hmm.
Yeah, so the vector that gets fit into DG, like that FA thing, is actually DFA, right?
Well, so, okay, what we really have here is this x prime vector. That x prime vector is going to be over here. X prime, it's also going to be here. So what we're saying is that if you're interested in what the composition does to x prime, right, that you can compare that with what df does to it, followed by what dg does to it. That make sense? So what dg is acting on, let's look right here in the picture. dg is acting on this, what I'm calling y prime, but y prime is df times x prime. It's not df. df isn't a vector. df is a matrix, right? So dg is acting on df times x prime.
Okay.
Yeah. Yep.
But like, why do you write it this way? FA just makes it seem really simple.
Do I now?
Like, why do you write it this way? Why do you represent dfax by just FA?
Well, I'm not writing this as this, right? I'm just observing that what I have written down here is the sort of the succession of the development of these vectors. But since they do the same thing to x prime, these two matrices must be the same matrices, and it's just easier to recognize the fact that these are the same as matrices.
Oh, okay.
Yeah, it's just just an easier way to write it.
Yeah.
Yeah. Okay. All right. Okay, so let's talk now about the partial derivative. The partial derivative. We're interested. How am I going to compute this partial derivative here? Again, that is a partial derivative that's involved in the composition. Right? So it's going to be one of the elements of this matrix. Right here, this is the derivative matrix for the composition. This is all the partial derivatives of the composition. Apparently, we're looking for one of them. Which one are we interested in? And the way we're going to figure this out is to recognize, I can't quite fit this, there we go, to recognize that we're taking a partial derivative of Z3. And you'll see right here, Z3 is my third output variable. Okay, remember from the construction of derivative matrices, output variables correspond to rows. So because we're looking for the third output variable, we're looking for an element in the third row of this matrix. Which one? We'll get to that in a second. But third output means third row, means it's one of those numbers. And then likewise, we're looking for the partial with respect to x1. x1 is the first of our input variables. Input variables correspond to columns. So, first input variable means we're looking for the element in the first column. And so the number that we're looking for here, specifically, this partial derivative is in the first column, third row. That's this number right there, and that is 3. Everybody happy with that? Yep.
So that's the derivative matrix at the point, or that vector 1, 2. How do you know that's the partial derivative at all points?
It's absolutely not.
It's just at that point.
This is everything. Yeah, that's right. So these derivative matrices, you'll notice, were evaluated at specific points. Yeah. So yeah, everything that we're writing here applies only at those specific points.
Asking for the partial at that point.
Yeah.
Okay.
Yeah, that's right. So one thing mathematicians will do when there's, let's consider the two alternatives of what might I have meant when I wrote this down. And by the way, technically you're right. You got me, right? I should have written partial of Z3 with respect to x1, open parentheses, at the point 1, comma 2. But if I had wanted you to compute the overall partial as a function of x1 and x2, there's obviously not enough information to determine that. So I couldn't have meant that. Does that make sense? And that's an excuse, right? This is a little sloppy, but you're going to see this kind of sloppiness sometimes. It's not rare. Yeah. Okay. Yeah.
That notation where you write compute d g of.
Yep.
That's d g like at 1, is that what it's supposed to be?
Yeah, that's right. So that's right. So we're looking for the derivative matrix of the function that is g compose f, and then we want to evaluate that at the point 1, 2. Yeah, that's right. That's right. All right. So moving along, there's a couple of special cases I'm going to point out. So these are just special cases. Let's think about these specific special cases. This is a composition of functions. I have this, 2 functions I'm putting together. You'll notice, though, that here my domain is one-dimensional. All right, so the succession of 3 spaces, right? 2 functions composed, but the first space is one-dimensional. Okay, what does that mean? How does that affect our interpretations of things? Well, a couple of things. First of all, this original function, this first function here, now this isn't really a multivariable function anymore. It's got multiple outputs, but we have multiple outputs that are functions of just one variable. And the very first observation I'm going to make is that means the derivative matrix for that function has a single column. Next observation I want to make. Since we have one input variable, that means that really this is a parametric curve. Position is a function of one parameter. Again, I like to think of that as being time, just for kind of physical analogy, interpretation, convenience. So this is a parametric curve. We're looking at the derivative matrix of a parametric curve. We just talked about that last time, I think it was. Derivative matrix of a parametric curve is the velocity vector, right? So I can interpret this, wrong color. I can interpret this as being the velocity vector of that first function. Is that cool? All right. So likewise, let's look at the composition. The composition, again, several same things I can say. The composition has one input variable. Therefore, the derivative matrix is going to have one column. Further, we have, in fact, position as a function of one variable, which means that this is also a parametric curve. This is now a parametric curve in Rm. Okay? So altogether, then, what I really have is that this represents a velocity in Rn, and this represents a velocity in Rm. And so, give me a second. What that means is that I can make an interpretation of what the derivative matrix is doing. What the derivative matrix is doing, according to what I just sort of thought through, what df is doing is it's multiplying by the input velocity to f, and what comes out is, well, the output velocity from f. And I'm going to say that's old news. This is something we already knew, right? This is an interpretation that we made back in section 2.3. Derivative matrices turn input velocities into output velocities. So this is not news. This is something we already had established. But it is kind of nice sometimes to notice that when you have a new result, notice that sometimes it'll recover old conclusions. Yes?
My question was about, I thought derivatives correlated with position and not acceleration. So, I thought integrals were, your progression from, you start with acceleration back to position, whereas derivatives was the opposite.
So the distinction we have to make is that what I'm doing here, this is a derivative, right? But I'm not taking a derivative of this velocity. I'm taking the derivative of f. And it's just that what derivatives do is they turn input velocities into output velocities. Yeah, so this is a derivative. And then you're right. True. This is also a derivative, right? But just to make the interpretation that we're making here, what we're doing with this derivative is we're we're going to interpret this one over here as being a velocity, and just recall that derivatives turn input velocities into output velocities. But very importantly, I'm not taking a derivative of this velocity.
Okay.
Does that satisfy?
It's a scalar.
I'm sorry?
It's just a scalar at that point?
No. It's not. Nope. There's no scalars involved here. This is a matrix. Derivatives are matrices broadly, and what derivatives do to other things is derivatives turn input velocities to output velocities. Okay, yeah, we can talk after class if you want. Yeah. Okay. All right. Okay, so example, let me be really quick with this example. It's straight up what we just talked about. And by the way, again, all we just did is talk about how the interpretation we just made was old news. Right? Again, we know from section 2.3 that derivative matrices are what you multiply by input velocities to get output velocities. And that's all this question is about. This question says, hey, suppose you have an input velocity, 3, and you want to know what is the corresponding output velocity. Right? How are you going to compute this output velocity? Well, the derivative matrix is what does that. And so you've got to take your f and compute the appropriate partials and assemble and then plug in the given point. And then that's what you put here, which, of course, we just did the arithmetic of, and it's, turns out, this right here. So all this example is saying is, yeah, exactly what we had on the previous page. The derivative matrix multiplies by input velocity to give output velocity. Yep.
How'd you find x2 and x1?
Do what now?
How'd you find
x2 and x1? Oh, yeah. So we are at the point wrong color. We are at the point 2, 1, and that means that this is 2, 1, and so the point where I need to evaluate is 2, 1, which means I guess I didn't write it down anywhere, but yeah, when I compute these partial derivatives, x1 is 2, x2 is 1.
Oh,
Plug those in to get this.
Okay.
Yeah. Okay. All right. Okay, next special case. Now this is a special case of the special case, and again, this is just going to recover something we already knew, and it's going to do so by way of making an observation that we've already made. But I think it's worth pointing out. So we've already addressed that when you have a single input, that you're going to have a single column there, and you're going to have a single column here. And notice in this new special case, we're furthermore going to consider what happens when you have a single eventual output. Right? So real valued, not vector valued. And keep in mind, output values correspond to rows. And that means that this matrix has a single row, and likewise the composition has a single row. So a couple of consequences. For one thing, the question is rate of change of one variable with respect to another one variable. The derivative we're looking for is a Calc 1 single variable, world's most boring derivative, just dy dt. More interestingly, though, this derivative, the derivative of f in this case, the second function, has a single row. And if you think about, we've got a mess now. If you think about this operation, when you're multiplying a single row matrix times a vector, remember that's morally a dot product, right? And okay, these are technically different things. This is a derivative matrix. This is a geometric vector, which if you're going to write it as a matrix is a column. So I guess arguably this is the transpose of that if you want to, be fussy about it. But the point here, the better point I'd say in this case is the arithmetic of how you multiply, this times that, plus that times that, plus blah, 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 plus that times that. It's the exact same algebra, exact same arithmetic as if you do this dot product. Yeah.
I'm a bit confused as to what we're trying to compute
Yeah, so I guess I didn't write that down, but we're trying to compute the derivative of the composition, which is dy dt. That's our, yeah. I didn't put it in the statement of the question. I probably should have.
And you compute dy dt by using the partials of what?
Yeah, by just using the chain rule, right? So realizing that y computed from t is a composition, you just write down the chain rule, and this is just what the chain rule happens to look like, because again, only one input, only one output. And then we make the observation that a single row matrix product is effectively a dot product. Yeah. Yep.
You were saying how like the gradient of f is the transpose.
Yeah, if you want to get fussy about it. I mean, so a vector, if you want to interpret a vector as a matrix, it's a column vector.
Oh,
it's a column matrix.
So before it's just multiplied and now.
Yeah. So I mean, if you want, because notice when I do this multiplication, right? This is a vector, right? But it's a column, right? So just to make things work out, if you're going to interpret a vector as a matrix, it's as a column. Yeah. Okay. Last question we got to go.
Can I ask a question about the above example?
Okay.
Why is df? Why is the first row x2 and then x1?
Yep, just taking so this row is going to be the gradient of the first output, and if you take the x1 partial, you get that. And if you take the x2 partial, you get that. Yep. All right. So yeah, another example. This one is, honestly, I don't even know why I still have this example in here. The only thing that's different between this example and the previous is that instead of writing the application of the chain rule here as a derivative matrix multiplied, I'm writing it here, because it's a real valued case, as gradient dot. So it's the same, structurally it's the same. We have an input velocity, we want an output velocity. We do so by applying the derivative, and again, I'm just interpreting the derivative here as dot product with the gradient, as we previously noted earlier, a few seconds ago, and as we previously noted like last week at some point. I don't remember exactly when. Okay. All right, the rest of this I think is pretty readable. Give that a look. Okay, here's a completely different way of thinking about the chain rule. First, I'm going to show how it follows from what we already know, and then I'll talk about how useful it is to sort of reinterpret the result in a different way. So here we go. As usual, we're going to talk about a first function that'll have a derivative matrix, and then a second function that you can see we're composing, because what comes out of the first goes into the second, right? And so that second function, its derivative matrix will be like this, and then you can think about the composition, and the derivative matrix for that composition is the product of the individual matrices. So I haven't done anything new here. This is just recognizing a composition, documenting exactly what my variables are, and then fleshing out those derivative matrices, pointing out that they are in fact made out of individual partial derivatives. Okay, so this kind of combines several ideas that we've talked about at various points in the past. Now I want to address, though, a pretty common scenario. Pretty common scenario is I don't really need to know the whole matrix. Sometimes, actually pretty often, all we need is to know a particular element of that matrix. If you think about it just from a sort of practicality standpoint, do I really want to have to compute the whole matrix just so I can get that one element that I want? No, that's way too much work. I don't want to do that. A lot easier just to try to figure out how we can compute one element at a time. Good news, we know how to do that. Whatever column that one element it is, that tells you which column of the right matrix you're going to be doing a dot product with. And then likewise, whatever row that element is in, that tells you which row of the left matrix you're going to look at. And then, old news, when you multiply matrices, it's row dot column. That's how you compute individual elements. Okay. So nice little punchline there. You get this equation right here. And what's nice about this equation is it gets right to the point, right? If what I want is that specific partial derivative, boom, right here. Partial derivatives for function arithmetic. That's exactly about as efficient as you possibly could how you're going to compute that thing. Okay, so it's a nice sort of, I don't want to say alternative. It's a nice special case to keep in mind. Now, there's a whole bunch of stuff I want to say about this equation, how to think about it. But before I get to that, I do want to give you a warning. A lot of students get this one wrong, surprisingly often. And as I've talked about this before, the more I harangue about particular landmines, the less students step on them. And so here we go. Here's what a lot of students do wrong. A lot of students start writing this down, and they get to here, and they're like, oh, well, wait a second. Those cancel, and this is what that is, and this is what that is. And, oh, so I must be done. And they just end it right there and don't write down the rest of this. And they're like, done. So does everybody see the temptation?
Yeah.
It's very tempting. Okay, landmine. This student just got 0 points on that question on the exam because it's really, really wrong. Now, very worrisome. Wait a second. What's wrong with this reasoning? And let me show you what's wrong with that reasoning. It's, frankly, partly the fault of notation. This notation, this Leibniz notation for writing down partial derivatives leaves a lot to be desired. It's a real problem in several ways. So in particular, looks like a fraction, doesn't it? When you have a fraction, you would expect that that's a fraction of well-defined objects. It's not. Very importantly, it's not. This thing right here, partial y1, is not by itself a well-defined thing. There is no partial y1. That's not a thing. So let me try to persuade you, in particular, whatever the interpretation you're going to make of this in the context of this setting. What is it in this context? And I'm going to try to persuade you that it is in fact a very different critter from this thing right here. That's a completely different thing. And the point here is that these, yes, they do both represent how much y1 is changing. The important point. Each of these is representing how much y1 is changing in completely different and incompatible scenarios. Totally different stories that couldn't possibly happen at the same time. So in particular, in this story right here, we're taking a partial with respect to y1. That means all the other y variables have to be constant. In this story on the left, the other y variables are all constants. Okay, fine. Now let's look at this story on the right. In this story on the right, well, wait a second. In the story on the right, we're changing xj, and all the other x's are constant. But wait a second. If you're changing xj, that's going to make not only y1 change, it's going to make all of the y variables change. Oh, color choices. Not constant. So these cannot be simultaneous scenarios, right? It doesn't make any sense. This y1, this partial y1 could not possibly be the same things. So you cannot cancel them. And it's absolute garbage to think that you can cancel those things. Does that make sense to everybody? Now, again, I blame the notation, and I didn't do it, right? It's not my fault. I did not create this notation. I've been complaining about this for decades, right? But it's completely howling at the wind. This is deeply embedded in the culture, and it's not going to change. And it's just an exercise in futility. So y'all have to just remember that even though this looks like a fraction of objects, independently well-defined things, it is not. It is a notation. It is a fairly unfortunate notation to represent, this particular process where you hold certain things constant and you take certain derivatives, and the notation as it's written is vaguely justifiable, but not really. So please, 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 please do not make this mistake. This cancellation is a bunch of garbage. And you will get dramatically wrong answers and your bridge will fall down. Everybody all right? Okay. Another thing that's particularly dangerous about this, you want to remember it's not about answers, it's about reasoning, right? So it's not just that your bridge will fall down, it's that the reasoning is fundamentally nonsense. It's fundamentally garbage reasoning, right? And so again, we do see this sometimes. We see students starting to write down this sort of coordinate version of the chain rule, and they get to here and they're like, "Ah, sweet," and they do like this, and this is on the page, and this is how they compute this composition part. Okay, that student who writes this down clearly does not understand what's going on, right? And so from the point of view, just from a grading point of view of, how much partial credit should that student get? The student clearly has no idea how the chain rule works. It's not good, right? So dangerous landmine. And so again, this is why I make a big deal out of it. I'm trying to make sure that nobody steps on this dangerous landmine. Please, please, please don't make that mistake. You cannot cancel. This notation is misleading. This nonsense that I have on the page here is garbage. Okay. Okie dokie. How are we going to make sense out of this equation? Here's what I think is a pretty reasonable point of view. If you want to compute the partial of zi, there it is, with respect to xj, there it is. Keep in mind partial derivatives means I'm going to hold all the other input variables constant. This is our little scenario then, and I appeal to your sense of process. If you start changing the values of xj, all of these y's are going to be changing by some amount, to be determined how much, but they're going to all change, and then one at a time, individually, each one of these changing y variables will contribute some amount to how much zi will change. And what we can do is we can look at each one of these paths individually. I can look at, when you change xj, how much is that going to contribute along the y1 path? How much will that contribute to the partial derivative that we're interested in? And then you do this for the second y, the y2 path, and then et cetera, and then finally you look at the last path. And if you add up all those individual contributions, then you will get the total amount that zi is changing. So let's look at these paths. Now let's take them one at a time. By what factor do changes in xj get magnified to result in the corresponding change in y1? Well, that's a partial derivative, right? The amount that the factor by which y1 changes, more than xj is that right there. That's what a partial derivative is. And then, but that said, from that, by what factor does zi change in comparison to how much y1 changes? Well, that's this factor right there. So altogether then, looking along this entire path, looking along the entire what you might call y1 path, that product represents the total sort of factor by which xj changes propagate along y1 to contribute to zi changes. So just to streamline everything then, corresponding to the y1 intermediate variable, in other words, looking at how much changes propagate along that path, you get that term. And here's one of the really beautiful things about how this is written down. One of the nice things about the notation. You can see that this term corresponds to the y1 path because there's y1s there and there. And then you can also see, 2 seconds, you can also see that we're looking at the eventual change in zi, and that we're looking at the change with respect to xj. So all of these terms are going to follow this pattern. In some sense, the zi is going to be there, the xj is going to be there, and then the intermediate variable corresponding to telling me which path I'm moving along will be sort of on this diagonal. Again, as if they cancel, which they don't. Right? But just kind of visually, cosmetically, it's a nice way to remember it. Did I see a hand? Yeah.
So the way to look at it, for example, for y1 to zi, so it's how much y1 is changing and what's that going to result in the change of zi? Or
Yeah. So this is going to change by some amount, and this is going to change by some amount, and along this arrow, we're just looking at the factor. By what factor would I multiply this change to get that change? That's right, and that gives you this factor right here. Yeah. Okay. Yep. Okay, so nice little sort of point of view, and again, just to further streamline, for every intermediate, for every intermediate variable, there is a corresponding term, and et cetera, and then lastly, for the last intermediate variable, you get your last term. So I tell you what, I think it's a really bad idea to try to memorize this formula based on the symbols. For one thing, look at all the symbols. Oh my gosh, that's a lot. That would be really hard to memorize from rote. Don't do that. All right, that'd be silly. Also, if you memorize it character for character, that assumes that your functions are set up with their input variables being literally, as I've written here, named x1, x2, x3, etc. They probably won't be. Right? In practice, they're going to be named, I don't know, whatever makes sense in the context of what you're doing. Probably won't be named this. These probably won't be named that. These probably won't be named that. So you kind of, even if you have a photographic memory, this isn't the right formula most of the time. Right? What will always work is if you have a nice little diagram representing your original input variables, your intermediate variables, and your eventual output variables. And if you represent the partial in question by thinking about these intermediate paths, you can construct the chain rule as you need it, tailored exactly to the way the variables in your scenario are set up. And just write down, generate your own chain rule as needed individually every time. And I think that's the best way to do it. Okay. All right, so let's see an example. Here we go. We have, now I kindly set up the variables the same here. The x's and then the y's and then the z's. And again, don't get comfortable with that. It won't always be like that. But you can see that the f acts first because what comes out of the f is what goes in to the g, right? And so we can represent these functions. So y1 and y2 being f of x1, x2, x3. There's kind of that part of the diagram right there. And then likewise having the z's be g of the y's gives me kind of that part of the diagram, and there's our diagram. Now I haven't written all the arrows in here because most of the arrows, okay, fine, yes, y2 is among other things dependent on x1. I didn't draw that arrow because I'm not going to need it, and I wanted my diagram to be as kind of streamlined as possible. But that's my diagram, and so looking at the fact that I've been asked to compute the partial of z2 with respect to x2, you can see that all I really need, the only arrows I really need are those that involve my intermediate variables, y1 and y2. You can see it right there that those are the intermediate variables. And for the intermediate variable y1, aka for this path through y1, you get this y1 term. And again, you can see that it's the y1 term because of how y1 shows up in those partials. It's always the same little structure. right? And then likewise, we have what you might call the y2 intermediate variable, representing the y2 path through the diagram, which gives rise to this y2 term, again with the y2s showing up and consistently, and always that little point right there. Yeah.
So we have to always go through all of the intermediate variables.
That's right.
And then just go straight like.
Yeah, no, you got it. That's right, because through every intermediate variable, there is a path through which changes are going to be propagating, and you got to
So we're taking the sum of all of the changes.
Mm-hmm. The sum of all the paths through which changes can propagate. Yeah. Right. So here's your chain rule. Now again, I didn't memorize this formula right here. Right? How come I don't have a y3 term? Well, because there is no y3. Right? All right. Okay, so all that remains is to plug and chug. Now, just for fun, let's just do one of these. How do I compute the partial of z2 with respect to y1? Well, I have a formula right here. z2, apparently, is that. So if you want the partial of z2, with respect to y1, well, you take the partial of y1 cubed with respect to y1, and that is 3y1 squared. All right. Okie dokie. Okay. Gotta be really careful about one little dangerous little point. This is a point of notation. I'm going to spend hopefully as little time as possible on the single variable version of this landmine, this danger. This is, again, a dangerous little thing. The purpose of which is to point out the obvious, to convince you that this is a clear, well, of course, kind of situation. And then I'm going to point out that, yeah, by the way, the same thing's true in the multivariable setting. So back to single variable, and again, I know y'all are experts at the single variable chain rule. Here's a couple of functions, perfectly fine, nothing wrong with them, no problem. I can ask, hey, what happens when I compose them? And more to the point, what's the derivative of that composition? Perfectly reasonable question. Here's the nasty little bit that I didn't mention in the statement of the question, and that will not necessarily be mentioned. This is the answerer's job, not the asker's job. But I've written these two functions in a way that's perfectly legal, but is highly incompatible with the idea of composing them. If you think about it, when you compose two functions, what comes out of the first function had better be what goes in to the second function. So as it stands right now, it looks like I'm saying that x squared, the output from the first function, is equal to x, the input to the second function, and that's obviously not true. Right? So that gives rise to this ridiculous calculation right here. This is wildly wrong. Right? I was way too fast and loose in writing down the single variable chain rule here. I like the pithy phrasing that derivatives turns compositions into products, and so here I just wrote down the product of the derivatives. I computed these derivatives correctly, but I get a wrong answer. Because you need to evaluate the second function's derivative at the first variable's output, right? So this is the little, I'm sure you all remember this little sticky little point about the single variable chain rule, and using Newton's notation. And of course, f of x being x squared, that's what sort of wasn't present in that initial calculation. This does give you the right answer. But I think there's a much easier way around all of this. I think even this one that I write as being valid is unnecessarily confused and clunky. It is so much simpler just to recognize that, hey, check it out. I am indeed composing f with g. And when you compose f with g, what you call the input variable for the second one, that had better be, in fact, what comes out of the first one. Again, that's how you compose. What comes out of the first is what goes into the second. So I think this was fundamentally a bad idea right here, to write the g function in terms of that dummy variable. It suggests that I would have x as the input and the output. from f. This is silly. So this is super easy to fix this problem. All you got to do is just recognize that this is a bad choice and take this way of writing the g function and just rewrite it differently. Instead of writing g in terms of the dummy variable x, just rewrite it in terms of a different dummy variable, y. And it's the same exact function. Dummy variables are called that because they're irrelevant, right? They're just arbitrary names. I could just as well say g of Bob equals Bob cubed. It's a placeholder, nothing more. Right? So nothing happens when you rewrite, formally speaking. But what's nice about this is now I have a diagram that makes everything easy. I have 3 distinctly named variables like this. And I can play fast and loose with the chain rule by writing it like this. Those derivatives are easy to compute. And then all you have to do is, in fact, you don't even have to remember to plug in, right? How do I know, wrong one. How do I know I need to plug in for what this y is? Well, because I need my answer in terms of x. What is y? Y, being as is the input to the g function, well, it's the output from the f function. So it is x squared. And that's why that goes into that. You get the right answer, and all's well and good. We didn't even have to worry about forgetting stuff. The notation did it for us. Pick up here next time. See y'all later.